Hello everyone. In this session, I'm going to talk about how we are going to use the support vector machines for the classification purposes. So that's where we are calling it as support vector classification, and that too only when we have binary categories. If we have categorical but with two categories, a person defaulting versus non-defaulting, winning the game versus losing the game, various other aspects associated with the support vector classification, right? So where how I can very well use the support vector classification algorithms in R. Remember, this session is not a mathematically intense kind of a session. We will not go in depth in terms of derivations, proofs of each of the algorithms. We will try to see the implementation of each of these algorithms in R, right? So it's more from a business perspective. Objective wise, I have a data, right? I have a data wherein one of the variables is a categorical variable, and that categorical variable is having two different categories, let's say default and no default, or let's say a win and a loss. So we have one variable which is a categorical variable having two categories, and we want to try to understand based on the various attributes of that data, based on the various attributes of that data, can I build a support vector machine which can differentiate between the defaulters and the non-defaulters based on the existing data, and build a kind of a model so that in future, if I'm when I'm getting a new data altogether, new applications altogether, I should be able to differentiate which of these people will be defaulting and which of them will not be defaulting. So that is the basic intention of using the support vector machines for the binary classification purpose. So here we are looking at two major algorithms. One is called as a CSVM algorithm, right? The classification using the support vector machines, and I'm also using one classification SVM. So these are the two models that we are going to look at here, and both these models I would be implementing on a data which is associated with diabetes, right? A data that is associated with diabetes. So here we are talking about a set of people, right? Especially with respect to the pregnant ladies who are at different stages of pregnancy. We talk about their glucose levels, right? Their blood pressure levels, and a few more attributes. And finally, whether they are positive to diabetes or negative to diabetes. Now, based on that, I would like to build a model. Can I really assess or link the presence or absence of diabetes to one or more of these various attributes using a support vector machine? And because my response variable is binary, I can very well use either this one or this one to typically do the classification of the data, right? So that's how we would like to proceed. Let me load the data first, and based on that we will go ahead in terms of the understanding of the model. Alright, now let's look at this data, right? It's a diabetes data that is present in this particular folder. I'm loading it into a variable called diabetes, right? So if we want to look at quickly what is there as a part of the data, I can very well look at the structure of the data. I'm looking at the structure of it. So it's a data frame containing 600 observations of 7 variables. We are talking about different months of pregnancy for each of these ladies, their glucose levels measured as integers, the pressure measured in terms of integer again, their mass measured in terms of numeric values. So there are a few NAs that are there as a part of the data. Even the pedigree is measured in some form. So you could see the pedigree measurement out here. Age, again it's an integer. Whereas the diabetes is looking like it's a factor with two levels, negative and positive. So that is what is the data right now, which we would be using for building a relationship between the presence of diabetes vis-a-vis the remaining six factors. And we want to look at how the support vector machine can help us in terms of building a model and probably using it for the testing purpose as for prediction purpose as well, right? So a few more things regarding the same. Let's look at the summary of this. Summary of the diabetes to just understand if there are any kind of NAs. Yes, obviously there are 5 NAs under this glucose column, 28 NAs under this pressure column and 9 NAs under this mass column. So it's better that we omit these observations altogether. So probably what I'll do is I'll create a new, I'll overwrite the existing diabetes itself, wherein I am using na.omit. So omit all those observations where NAs are present. So I'm saying na.omit diabetes, the basic data cleaning pass. Now if you want to look at the summary of diabetes at this moment, you will see that the numbers might have slightly changed, right? So probably from 44 to 198, no NAs now. Pressure from 24 to 122, the mass from 18 to 67, and so on. Right, the pedigrees. So now you don't see any kind of NAs. Probably there are 372 people who are negative to diabetes and 192 of them are positive to diabetes. Alright. So now, if I have to get started with the CSVM algorithm, so we have to load a package called SVM path, right? Support vector machine path. And in that we will be using this function also named SVM path. So let's first install the package. So let me call install.packages SVM path. I'm installing this particular package. So as a part of this package installation, okay, the package is installed. So let's load the package as well. So SVM path as a package is installed as well as loaded. So here a few important things that I would be using. SVM path, the X values are my attributes, are typically the covariates, right, which are used for building the relationship to the response variable. The response variable needs to be coded as -1 and +1, whereas here right now it is coded as negative and positive. So let's try to change it as -1 and +1. That's one activity for us, right? So we can very well change it to -1 and +1 and specified kernels using the kernel function. So we'll see what is there as a part of this kernel function. What are the kernels that are being supported out here? So we can try almost all the kernels to see where the result is coming out to be much better. So let's get started with that task. So once that we have loaded this particular package and got the data, now I have to convert the levels, right? So probably let's do one thing. I can very well take the levels separately, right? I will very well segregate the input and the output. So what I'll do is diabetes dollar diabetes. I'll either I can rewrite it to that, or I can very well create a new variable altogether called y. Y, I will simply create it as diabetes dollar diabetes. Let me create the y as the diabetes dollar diabetes. Only that one single column. Let me take it into y. And now what is the value of the y that is typically coming? If I am looking at y, it is coming out as negative positive. So I can very well set the levels. I'll set the levels of y as -1 and +1, right? I'll set the levels because I want the values of y as -1 +1. So initially I will set the levels of y as -1 +1. So now if you see y, it comes out as -1 +1. So because these are the levels, I can very well convert them into numeric, right? So I'll say as dot numeric, as dot character. First they are character, first they need to be converted into character. So as dot numeric, as dot character of y. So based on this, I'm getting my y this time 1 -1, but they are now numeric. But I want this y as a matrix. So if you look at just the hint regarding the SVM path, you could see this SVM path help SVM as a regularization or a cost parameter C. So overall SVM path as such is fitting the entire regularization path for a 2-class SVM. So it's purely for a binary classification, right? It controls the amount by which the points overlap their soft margin. So we are talking about a cost parameter which actually is used for optimizing the distance between the groups. Typically either a default large value of C is chosen. If C is very large, the overlap is very minimal, or else a few values are compared using a value validation set. So now the way you are going ahead is SVM path X. X is a data matrix n by p with n rows and p variables which are columns. So that is what you have to give as an X. And y is a response variable with -1 and +1 values. That is why I have right now converted it into that particular set. Now at the same time, it's better to have y in the form of matrix. So as matrix of y, I'll simply take. So what difference does it make now? It would be in a vertical order rather than as a vector. Then so I want this data matrix n by p, right? And at the same time, I'm talking about a kernel function, user defined function. I can give either poly.kernel, the default with parameter set to default. So the default with parameter set to default to a linear kernel and radial kernel. So I can give two important information out here. Either I can give a polykernel or a radial dot kernel. So these are the two inputs that I can give out here. So we will try both of them. right? We'll have a polydot kernel as one of the models, and we will also have a radial dot kernel as another model, right? We can even compare between the models as well. So those are the three things that I want to give as an input. All others I can very well take it as default. So the now commonly used kernels, we know we can talk about, in this case we are using poly or radial. I could also use a linear kernel or even a sigmoid kind of stuff. Now, coming to the steps in terms of executing this decision, initially I have to load the SVM path package, which we have already done. I got the necessary data. The response variable here needs to be a binary response variable. So we had it as negative and positive. We have done a preliminary inspection of data using the summary function. Tried seeing if there are NAs as a part of the data. In fact, we did have NAs. So we tried to use na.omit to very well remove those NAs from our data. And now we are trying to build the model only with the remaining data. And the response variable, we have converted it into minus ones and plus ones. So even that step is taken care of. Support vector machine kernels, whatever, whether it is a polynomial kernel or a radial kernel, they actually depend, internally the calculation is, they depend on the inner product of the attribute vectors. So there is a kind of multiplications that are happening with respect to the attribute vectors. And because of this kind of multiplication scenarios, there is quite a good possibility that large values, if an attribute is having a large values, it may result in a very large multiplication value, product value. Which means if the attribute values are large, they are going to influence my classification very heavily compared to if the attribute values are small, absolute values, right? If the absolute values of the attributes are large, they are going to influence my classification quite heavily compared to those attributes which are having smaller values. Which means in this case, just because let's say the glucose levels are much higher, right, ranging from 44 to 198, they are going to influence the attribute, they are going to influence quite heavily compared to let's say a pedigree which is having values lying between 0.07 to 2.42. I don't want any particular variable to influence the decision just because its size is higher. So that's where we don't want to get into that kind of ambiguities or confusions with respect to larger variables impacting the classification heavily. So we try to get into the process of scaling the stuff, right? So when we are doing the scaling, I want to omit that particular process. So basically what I am doing is, initially let me take diabetes 1, where I'll remove my response variable from it. So I'll say diabetes all the rows minus all the columns minus the seventh column. Omit the seventh column. So if you are looking at diabetes now, diabetes 1, it does not contain the seventh column. Now here you could see the sizes are very widely differing. Now this is where I say let me do a scaling. We have a scale function which will do a normalization, x minus mean of x. So typically the scale function says it converts it into a z-score. Z-score is nothing but each observation x, it subtracts the mean of x from it and it divides it by the standard deviation of x. That is what we are calling as a z-score. For each of the variables, for each of the attributes, we are going to compute the same. So I'm going to look at it as diabetes 1 is nothing but scale of diabetes 1. So if I look at it now, the first few observations of diabetes 1, I could clearly see that the ranges are more or less in a similar range. Very narrow difference that is existing between the values. Right? So that's what we do generally to make sure that size really does not influence our decision with respect to the classification. And once we are done with that process, now I have to split the sample data into a training set as well as the testing set. So now for that I need to know how many rows of data is there. So I'll typically find out n row of diabetes 1 to see how many rows are there. Yes, there are 564 rows. So approximately 70% of it, I will take it as a part of the training data. The remaining 30% I'll take it as testing data. So almost 395 observations, I will take it as the training data, and the remaining whatever 169 observations, I would take it as a part of the testing data. So that is what I'm going to perform out here. So for that, it's better let me use the seed function just to make sure that the random numbers are consistent. So I'll use a train as a variable which will randomly select 395 observations between 1 and 564. So for that I'll use the sample function. So I want to pick up a sample between the numbers 1 to 564. I want to pick up some 395 observations where there is no duplication. So replace equal to false ensures that all the 395 numbers that I am picking, they are all unique. Right? So that is what going as a part of the train. Now I can very well create my training data. I'll call it training data, which is a subset of the diabetes 1, wherein I am considering only the rows that are selected as a part of the train and all the columns. That is what I am calling as a training data out here. And I'll also call a testing data, which is again a subset of diabetes 1, where I am considering the rows which are not there as a part of the train, which is why I am calling it as a minus train. Omit those rows which are there as a part of the train. That is where we use the minus train, and I'll select all the columns. So we have those rows which are the part of the training data considered as a part of considered as a part of the train data. The remaining are considered as a part of the testing data. So we have broken the data into training and testing sets. Now it's time for me to go ahead using the SVM path function. So we can try different kinds of kernels. As I have said, we will try the poly.kernel once, and we could also try radial.kernel. See what is the kind of response that is coming out in each of these models. Right? So I have to specify the training data is both for X as well as Y. Oh, even for Y, I'll say train Y, wherein I have to take a subset of Y, right, wherein I am taking the train and all the columns. Only one column is there as a part of Y. So I am taking train Y as a subset of Y, where only the train is considered, and test Y, again I am taking a subset of Y, wherein minus train is typically considered with all the columns. So I have a train Y as well as a test Y also. And now I can use the SVM path. But of course, here there is a simple catch which is saying set within that SVM path function. If you set trace equal to false, for each iteration that it is doing, we have already discussed that SVM path actually goes with an iterative kind of a procedure. So every time it does not just start printing the results onto the screen, and our result will not be that complicated, and our screen will not go that complicated. So that's where it's better to set trace equal to false apart from all the other parameters that you are giving to the SVM path. So I'll say fit poly SVM. So I'm trying to fit a polynomial kernel. So let me call simply fit poly. So I have to use the function called SVM path. The X values are coming from the training data. I'm trying to build the model only with the training data. So the X values are coming from training data. The Y is coming from training Y. So that's where I have used train Y. And my kernel dot function, I am setting it to poly dot kernel. So we are using a polynomial kernel for this example, right? I don't need to put it in codes. I'll say function is polykernel, kernel function is polykernel, and let me also set the trace equal to false so that all the output will not be directly printed out onto the screen. So this is how the overall fitment is done. But at the same time, let me also parallelly bring out fit radial, which is the radial kernel I am bringing in. So all I am changing out here is radial dot kernel. So we have two functions that we are fitting. So convergence warnings are coming out here, but let's try them out. So I don't think there is an error, it's only a kind of a warning that has come out. So we have fitted a polynomial kernel as well as the radial kernel, right? So now once this is there, we are trying to look at the regularization path. Okay, before that let's try to see what this function has typically given, what this model fitment has come out. So this is how the fit poly has come out. These are the different iterations, right? So the different observations have been picked up on a random basis, and for each one of them the parameter lambda is typically understood, the value of lambda, and finally the error rate is also computed. So you could see for different iterations, you could see that the error rates are different. So probably it came down to 99, 98, 80s, right? 87, 86, 85. The error rates came down to 85. Basically this error of 85 or 84 is typically the misclassification part, right? This error that is being displayed is more associated with the misclassification part. So the lesser is the error, probably I see a few 83s, so that is the level of misclassification. So typically wherever the error is the minimum, I'm looking at that particular set of iterations where the misclassification rate came out to be the minimum most possible. Now this is where I am trying to identify where in which all iterations the error is the minimum most, right? So if you are trying to look at it with this fitted model, right, I'm trying to find out. So what I can do, I'll say with the fit poly with this particular model, I really want to see which particular iteration. There are 160 iterations that has come out. So I want to take the subset of these errors, right? I have the subset of all these errors within this fit, wherein I want to really find out where the error is typically equal to the minimum of the error. Right? I'm trying to find out the minimum value of the error, and I'm trying to take those which rows are typically containing the minimum value, and I want to get that particular value of the error where it is coming out to be the minimum most. So I could see that the minimum most error is 85. 85. So is this fit poly? I really need to identify where the error is the minimum most. Where did it go wrong? Oh, here I need to use double quotes. Why did I not get 85? That's what I'm wondering. Okay, error equal to minimum error. So we are comparing it with a value, so it has to be double equal to. So here I am getting that there are almost 7 or 8 rows where the value of 83 is present. So basically store this, let's say, as a part of your variable called error. We'll use them later because out of these 8, which one I have to choose, right? Which iteration I have to choose. So that's where I'm typically storing this as a part of the error, right? And I really want to know which rows contain this particular error. So I can very well get as the error rows. I want to see which rows are typically, so I can very well talk about which and all these things. Right? I can very well look at the which and see which rows are typically containing. Okay. So it's better that if I want error rows, min error rows, I'm trying to use the which function, wherein I'm trying to compare the fit poly dollar error where it is equal to the minimum of the error, minimum of fit poly dollar error. So I'm trying to see which rows typically are having the minimum error. So I could see that the min error rows is typically coming out as, okay, there is a 74th row that is containing a minimum error, 75th row, let's try that out. 74, yes, this is containing an error of 83. 75 iteration is also containing error of 83. Similarly, at somewhere here 125, 126 kind of numbers also we are getting 126, 127 to 131. Even those are your minimum error rows, right? And now we want to find out the lambda value corresponding to each of those error rows. That is what we are calling as a regularization parameter. So we want to find out that particular row with the least value of lambda. So that's where we are trying to first get the lambda values corresponding to each of these minimum error rows. So the lambda error rows, lambda min error rows. For each of the minimum error rows, I'm trying to get the lambda value. So I'm getting it as fit poly dollar lambda, right? I'm getting fit poly dollar lambda, and I have to take a subset of that fit poly dollar lambda corresponding to each of these min error rows. So obviously I'm getting the lambda values for each of these 8 observations. The lambda is 37 point something, 37 point, 12 point, 11 point, 10 point. So these are the lambda values that I am getting corresponding to each of these. So I can very well take the minimum of these values, right? So minimum lambda, min lambda row. I'm trying to find out that particular row which is having the minimum lambda. So I'm taking which. Again, I'm applying the which function, wherein I'll use fit poly dollar lambda. Within that, I want to take within that fit poly dollar lambda. I want to look at only those min error rows. So I'll take wherein I want to get the minimum value out of these, right? So I'm taking fit poly dollar lambda, out of which I'm trying to compare for each one of them fit poly dollar lambda of, I'm looking at all the minimum error rows. So I'll take out of all these particular rows where the value of lambda is the minimum most. So I'm taking it as the minimum of, again the same stuff. I want to get the minimum of all these values. I want to get the minimum of this. So based on this, I am getting my min lambda row typically as the 8. The 8th one, oh, I have to, so out of these 8, it is working out like the 8th one is having the minimum lambda. So I can very well go back, right? This is the minimum lambda. The 8th row is having the minimum lambda. So based on this, I can very well get the lambda value. The lambda value is nothing but lambda minimum rows. I'll take the lambda minimum rows, and out of this I would try to get the subset which is associated with this minimum. So my lambda value is working out to 10.89. Right, so for this particular purpose my lambda value came out to 10.89, and what we typically observe here is, in case of this particular classification, the lambda that we have got is actually the inverse of the lambda that we have got. If you look at the process, okay, compute the entire regularization path for the SVM cost parameter along with the classification error. The different lambda values are being displayed along with the classification error. Now I am using the width method to identify the minimum error. Minimum error is nothing but number of misclassified observations as well as the regularization value, which is the penalty parameter of the error term. And that's the reason I wanted that penalty parameter to be as least as possible. So within that least error, I have looked at that particular value of lambda that is the least possible thing. So I am identifying the least regularization value, which is the lambda value, which worked out to 10.89 out of all those observations with the least error, and I have assigned it to something called lambda. And this is called as a kernel regularization parameter. Coming to it, the SVM path algorithm typically reports the inverse of this particular number. So what is that I am doing based on this inverse? I am getting the parameter value simply as the reciprocal of the constant that I have typically got. So once you have got this particular lambda value, you can very well go ahead in terms of doing the prediction on the test data. So we can very well go ahead in terms of doing the prediction on the test data. So we'll say pred poly, where I am trying to do the prediction with respect to the polynomial kernel function. So I'll use predict. The model that I am using is fit poly, and the new values of x that I am considering here are the test data. That is what is the new value of x that I am considering, right? I am looking at the x values from the test data, whereas here the x that I am considering is without my values, right? That's where I'm taking only the test data. I don't have the response variable out here. And the lambda that we are talking of in this case is this 10.89. This is the value of lambda that I would be using for fitting this model, and the type I want is the class. The class typically saying whether it will belong to -1 or +1. So based on this, I am getting my pred poly. If you quickly see what is this pred poly, for each of them I am getting the values of either +1 or -1. -1 indicating a negative, +1 indicating a positive. So based on this, I can compute my table to look at the accuracy part. The predicted values denoted by pred poly, and the actual values are coming from y. So train y, right? I can directly take it, no, test y. Based on the testing data, whatever are the y values from the testing data, that would be my actuals. So I can very well create a table using this DNN, where the headings I can put, the first one is the predicted values, whereas the second one is our predicted class, whereas the second one is the actual class. So I'm taking both the predicted class as well as the actual class. What has happened? Yes, I have to put one more bracket. So overall coming out that 96 and 38, which is saying that 8 and 27, they are not classified properly. So if you look at the total misclassification rate, the error poly, if I am using this error poly, it is nothing but 8 plus 27, 35, divided by 35 plus 134, 169. So in this case works out that the misclassification rate, here the misclassification rate is around 20%, right? In this model, the misclassification rate, when I am going with a polykernel, the misclassification rate for the diabetes prediction has come out to 20.71%. So approximately 80% is the accuracy of the model. Around 20.71% looks like the error associated with the model because of the misclassification that is occurring. So that's how we can go ahead using the polykernel. But same kind of process now, I can very well go ahead with my radial.kernel also to see in which case the error is coming out to be higher and the error is coming out to be the lower. So in this case, at least the error is to the extent of around 20%, right? Now let's try the radial kernel as such. I think I have already used fit radial, right? Let me just check. Fit radial, yes. So this fit radial took 364 of the iterations altogether, but wow, the error is 2 in some cases. So the error is too less when we are going with this radial kernel function. The misclassification rate is much lesser in the process. So I want to first identify what is the minimum value of this error. So one step that I can very well go with is I can very well find out the minimum error just like the way we have done earlier. So I'll use the width and fit radial. With this fit radial, I'm looking at that particular error where the error value is equal to the minimum of the error. So I'm looking at where the value is the minimum most, right? I'm looking at where the error is the minimum most. So based on this, I'm getting that my error is 2, and in these many iterations I got the error value as 2. Now I want to look at all these rows where the error is minimum. So I'll call it as minimum error rows, which will give me using the which function, right? Using the which function, fit radial dollar error is equal to the minimum of the fit radial dollar error. So I want to get those rows where the error value is the minimum. So I'm getting here, these are the rows where the error values are the minimum, right from 271 to 80. So these are the iterations where the error values are the minimum. And based on that, I really want fit radial dollar lambda. I want the lambda values of all of these. So I want the fit radial dollar lambda of all these minimum error rows. For each of these rows, I want what is the value of the lambda. So I can call this as lambda min error rows, right? I'll call this as a variable lambda min error rows, where I'm getting fit radial dollar lambda min error rows. So based on that, for each of these rows, the lambda that I am able to identify is, these are the lambda values that I have identified for each one of them. And now I want the minimum value of the lambda. So I'll say lambda is something, or probably a lambda radial is something which is the minimum of the lambda min error rows. I want that particular minimum value. So based on that, I'll get the lambda radial here as 0.124. That's the minimum most value. So I would like to use this particular value of lambda, and at the same time when I'm going with the error, it is when I'm using the error on the training data, this model has given 2 out of what is that 395. So the error rate is hardly 0.5% on the training data, only 2 misclassifications, whereas in the earlier case the error was to the extent of, when we have used the other function, the error was to the extent of 83. So in that case, when we have used the polykernel, the error was the minimum most error was 83 misclassifications out of 395, resulted in 21%. But when we have applied that model on the testing data, the error came down to, the error is somewhere around 20%. 20.7%. So probably there is not much of a difference in the error between the training data and the testing data. Whereas here it looks like the error or the misclassification on the training data is only 0.5%. Now let's see if the same is the case in case of the testing as well. So let me call pred radial, where I am doing the prediction of the radials using the predict function. Fit radial is the name of my model out here. The new x values for me are the test data. Those are the new X values for me. The lambda in this case is the lambda radial, which is same as, what is the lambda radial here? It is 0.121243. So that is my lambda radial, and I am typing in the name of the, I want the classification to be -1 or +1. Based on this, I would like to look at the table wherein I am considering the predicted value, pred radial, and I am also taking test Y, which is talking about the tested output values, which is the actuals, and I am trying to name, if I don't want to name it. So one side we have the predicted values and the actual values. So this is what are the numbers. 99 and 5, they are correct predictions, whereas 60 and 5 are erroneous predictions. So here the error rate is coming out to 65 divided by 169. So in this case, the error rate, when we are applying this radial kernel on the testing data, the error rate has shot up to 38.46%, which is a clear indication that in this example, the radial kernel is a lot of overfitting has happened, right? Overfitting has happened because on the training data, the error looks like only 0.5%, whereas when the same model is applied to the testing data, the error shot up to 38.46%, which is a very, very big jump. Whereas when we have used polykernel, on the training data, the error was around 21%. On the testing data, it's around 20.7. There's a kind of consistency in the way the error has been observed between the training data as well as the testing data in case of the polykernel, whereas when we have used the other kernel, which is the radial kernel, we got into a very wide difference between the training data and the testing data. So in this case, it looks like the polykernel is much more appropriate for the classification of the data. And what we could clearly observe is the error that is resulting in this process is approximately to the tune of 20%. That is what we should understand when we are going with using the CSVM model for binary classification. So if there are any other methods, probably we could have used the decision tree for the same purpose, right? We could try logistic regression, we could try probit model. There are different models which can be used for the same objective. So this is where I can try all the models, and with the same set of training data, same set of testing data, and wherever I'm ending up with a much higher accuracy on the testing data would be the model of my choice for the future prediction purposes. So that's how I can use the CSVM for a binary classification purpose, right? Now, the same thing, I would like to use another model, which is the one class support vector machine, again from a binary data perspective itself. The other algorithm that I want to look at in this scenario is the one classification SVM, which can very well be implemented using the package E1071. One classification SVM can be implemented using this package E1071 with the SVM function, right? These are different algorithms, right? We may not be interested in the mathematics of each of these algorithms, but obviously when I'm trying to implement these algorithms for my data, especially when I broke the data into a training data and a testing data, I'm more interested in seeing which of them is performing much better with respect to the testing data, right? So let's load this package E1071. I'm loading this package E1071. Okay, I have to give it in quotes. right? So this package E1071 is installed, and here we are going to talk about SVM as a function, which we would be using for various other support vector machine classifications as well. But quickly, if I have to look at what this SVM function is typically containing, I have to first load the package. So library E1071, and then I will question the SVM. So SVM is a support vector machine used to train a support vector machine, this particular function. It can be used to carry out general regression and classification. So I can use both the purposes. The same algorithm I can use to carry out both general regression as well as classification, as well as density estimation. And this is where the formula I am trying to provide, I can use either as a formula or I can use them as x and y values. Now I can very well provide the x values, especially when I am looking at the classification directly. I can provide the x values, which are the various parameters. So I will ignore the y part. I'll only look at the x values. If required, I will be doing the scaling. The default itself is scaling will be performed here. So I don't need to explicitly use the scale function. The scaling will be performed by default, right? So the scaling will be performed. The type is, again, it can be used as either classification or for regression purpose, or in some cases I can use it for novelty detection also. Probably in this case, if I want, I can use it for a novelty detection purpose as well. Depending on whether y is a factor or not, the default setting for type, classification. So for classification, I will use it as C hyphen classification or EPS regression, depending on whether it is whether the y value is a categorical value or a numerical value. So for novelty detection, which I can use in this case, I will use it as one classification. Then the kernels. If you look at the kernels that are used for training and predicting, I can use any of these kernels: linear, polynomial, radial, and sigmoid. These are the different kernels that I can very well use in this case, right? I can use either linear or polynomial or radial or sigmoid. And again, if I'm going with a polynomial, it's better that I define the parameter for the degree, the d part. And similarly, for some kind of kernels, I require the gamma values, right? If you have seen the if we see the formulas associated with each of these kernels, which I have showcased here, so I require the gamma for the radial basis as well as for the sigmoid. I require the d value as a parameter for the polynomial kernel. I also require r as a parameter for the sigmoid. So again, different mechanisms go with different sets of parameters. So I need to really provide those parameters as well. Otherwise, there are some defaults that are typically being taken, and using those defaults, the entire set of classifications are done. So here I would be using this one classification mechanism specially for novelty detection purpose, identifying the pattern in the data. I'm using it for the purpose of novelty detection. So we have the attributes that are used to train the model. The type, we will set it to one classification, as I have already highlighted. The kernels, we can try all the four different kinds of kernels. We can try the linear kernel, we can try the polynomial kernel, we can try the radial basis kernel, as well as the sigmoid kernel. All these different kernels can very well be tried, creating different models. and based on that we can very well evaluate which one is working very well for our data. So we have already loaded the E1071 package. The necessary data that I want will continue with the same data. So I have even performed the preliminary checks on that data as well. Now for executing this, one of them we should make it to true. Here it is like a binary. So one of the categories as one classification class, I have to look at either the diabetes being positive or negative. One of these two, typically let me consider the positive as a one classification class and create a variable. The variable I want to call it as is positive or something. So I'll call this variable as positive. So wherever the value is positive, I'll assign it to a value true, and all other values I'll assign it a value false. So let me start through the process. The diabetes, the original one, right? So this one, when I have to go ahead with the process, again let me set the seed so that the random numbers are picked up relevantly. So I'm setting a seed of 1000. Now let me just check what is there as a part of diabetes. The head of diabetes is containing all these 7 variables, including whether the diabetes is positive or negative. Now what I want to do is, out of this one of the class, especially the positive class, I want to take it as true or false. So this is where I'll create another additional variable, diabetes dollar positive. Right? I'll create a new variable called diabetes dollar positive, wherein I am actually checking, right? I have to set this particular value either as true or as false. So that's where I'll say diabetes dollar positive of, I'll take a subset where diabetes dollar diabetes, where this particular value diabetes dollar diabetes is equal to POS. Wherever the diabetes dollar diabetes is equal to POS, I'll set it to a value true, and wherever this is equal to any G, right, wherever this is equal to any G, I'll set it to a value false, just for you to test out what has occurred in the process. Let's quickly look at the head of diabetes after this particular step. So we got one variable called positive, which contain trues as well as false. So quickly I can look at the table. So this you can do even if there are multiple categories. We'll do a novelty detection part. So I am doing a table diabetes dollar positive just to see how many trues, how many falses are there. So there are 372 false and 192 trues as a part of our data. Then we want to see, we want to create two different subsets, right? So we want to create two different subsets where we are talking of positive and negative. We want to create two different subsets based on positive and negative. So let me call a subset positive, where this whole value is equal to true, right? So I can use a subset function. I'm taking a subset out of this diabetes. I'm taking a subset of this diabetes where diabetes dollar positive is equal to true. So I'm taking that particular subset where the value is equal to true. Operator is invalid. Why is it invalid? For atomic vectors. Or let me take the subset separately. Positive is nothing but I'm taking from the diabetes, right? I'm taking a subset where diabetes dollar positive, diabetes dollar positive is equal to true, right? I'm taking that particular subset where that rows are taken and all the columns are considered. So that is what is my positive, and negative is again those set of rows which are again a subset of diabetes but which have the value as false. So I am splitting the data both into positive as well as the negative, right? So I have considered two different subsets, one containing the positive. If you quickly look at the head of positive, it contains these are the elements which are where the diabetes is only positive, or you could very well talk about the dim of positive, which talks about 192 rows and 8 columns, and dim of negative talks about 372 rows and 8 columns. So basically we have segregated. The reason why I have considered this additional step of positive, true, false actually is I could implement this process even for more than two categories. The same novelty detection I can do even for more than two categories variable, but still I have to consider that particular variable into a binary kind by assigning this true and false. That's one of the prime reason I had to go ahead in terms of creating a new variable called positive and assigning the values of true and false to it. Now, positive wise, I have 192 observations, right? And based on this 192, I'll create a training data as well as a testing data, right? So out of this 192, let me take the 70% of it, which is approximately 134. So I will call a training data train, which is taking random sample between 1 to 192, right? It will take 1 to 192. It will pull out 134 observations randomly where the replace is set to false, which means there is no duplication in those 134 values that are typically pulled out. So this is what has typically come out as a part of the train. So I will take the training attributes. Probably let me call it as train data, where I will consider out of this positive, I'll consider only up to this attributes. I will not consider the response variables out here. So I'll consider only the attributes. So this is where I can very well say positive dollar train rows and only 1 to 6 columns. That would be my training data out here. I'll consider the positive. Out of this positive, I'll consider only those rows which are coming as a part of the train, and only the first 6 columns which are actually the attributes. Similarly, train Y, which is the labels associated with the training data, I'll take only the positive with respect to train, and I'll consider only the 7th column. So that is what is my train Y, and this is my train data, which is X. Similarly, I can very well have my test data, which is again from the positive, I'll take minus train comma 1 to 6, and I could also say test y is positive, and I'll take it as minus train comma 7. So these are the four initial set of values I'm bringing in. So we have chosen one of the categories as one classification class, created a variable to store the true and false values accordingly. Actually, I don't need to do this process if I am having only two variables, but because this model can two categories, but because this model can very well be extended to multi-category scenario also, one of those categories I should classify it as a one classification class for novelty detection, and based on that I should be creating one variable which will be true for one category and it will be false for all the other categories. So we have created two different subsets of data, one containing the true values and one containing the false values. Then again, create random samples as training data from the positive values, purely from those people who have a diabetes positive. From them we have created a training data set. We have separated the attributes, right? We have called train data separately and train y separately. Now we can get into the estimation of the model. We can either directly estimate the model using the default scenario, or we can actually get into the tuning process, either of the ways. So if we are going ahead with directly, right, if we go ahead directly in terms of assessing the SVM directly, right? You can very well use the SVM, because as we have discussed, in this SVM we are giving the X values, Y is null, scale is true, kernel is something that I have to set. But depending on the type of the model that we are using, let's say if I am using the radial kernel, I require the values of gamma, right? And I want to know what should be the value of gamma. By default, the gamma here would be set to, if we look at it here, the gamma, if is vector of x 1, else 1 by n column of x. That's a kind of a default setting for SVM. Right now let me actually go ahead in terms of first fitting the SVM directly by default, right? Then we can think of modifying it to see if there is any improvisation in the model. Fit initial radial. I'm going with a fitting of the initial radial function, where I am using SVM as a function. The attributes for me is the train data in this case. Y I don't need to consider, so let me set it as null itself. I'm not specifying any Y. I want to understand the pattern directly from the data. The type is something that I have to set it as one classification. That is what I have highlighted to you earlier. If I want it for novelty detection purpose, I have to set it as one classification. But here I will not consider the tuned parameters of nu and gamma. So these are the two parameters that we require for a radial basis. The nu and the gamma values we require. But right now I am not considering any specific changes to the value of nu. Nu I am taking it by default as 0.5, which it is considering, and gamma also, if it is a vector, if it's a vector, then the length is 1, otherwise it's 1 by n column of x. So the number of columns, so the number of columns are 6. So by default for this case, the gamma would be considered as 1 by 6, right? Because there are 6 columns of data. By default it would be considered as 1 by 6, and the new value will be taken as 0.5, and based on which I will go ahead in terms of the fitting of the model. And if required, I can do a cross validation, right? If you look at this if you look at this cross, if we can look at this cross validation, I can very well, k-fold cross validation is something which means the to just improvise the quality of the model. Different combinations of observations would be taken as a part of the training model, and different observations would be considered as a part of the testing. So the cross validation, I'll typically go ahead with the size of my model. So cross validation, I'll set it as 134, which is there as a part of my training data. So these are some of the things I would go ahead as a part of the initial fitment process. So this is my initially fitted SVM model for one classification purpose. So now if you see, it's a one classification model, 70 different parameters, 70 different support vectors have been typically created in the process. Now if required, I can very well go ahead predicting this model. We'll save all of them. So the fit initial radial model has created 70 different support vectors, right? And I have for each one of them. Now if I want, I can actually go ahead in terms of doing the prediction as well. If you really look at, right, if we really look at going ahead with the model, if I want to test it out on my, if I want to do the prediction there, so I can very well talk about pred initial radial. Let me see what is coming. Prediction value of the pred initial radial. I can very well use the predict function, where I am using the fit initial radial model. Right, I am using the fit initial radial model with the set of train data. So when I am trying to predict with respect to the train data itself, so this is what is the prediction that is coming out. So you could see pred initial radial is coming out like false, true, false, false, false. Now I can very well compare this with respect to my original data, right? I can very well compare it with respect to my original data. So it's coming out like table, and the predicted values, this is on the training data. So pred pred initial radial, and I require the true false with respect to my training, or probably you convert. So probably we'll call pred initial radial. Right now if I want to compare it, I am talking about if else, if this particular value, if the original value is equal to true, right, if the original value is equal to true, then let me call it as false, else let me call it as negative. So it will be considered as either positive or negative. So based on that, I will compare the predicted initial radial. The predicted value would be compared with respect to the actuals. The actual is coming out as train Y. So which is telling me that initially, without using any kind of improvisation to the model, the positive classification is happening like this, which means the error rate is around 66. So everything is getting treated as positive. Oh, so probably it would have been the case Let me again redo the process. That's not the case because we have a few false and few trues in the model. Probably the way we have written the true is looking like a problem. Spread initial radial wherever it is true. Let me just remove. Okay, right. So because here it is getting predicted as true false, whereas in my training data everything is true. So that's the reason the accuracy of the model is coming out to only 66 out of 134. That is what is the accuracy coming out, which is error rate is coming out to 66 out of 134, working out to 49.25%. Whereas the same thing if I go ahead with respect to my testing data, the same model, right? The same model, if I have to do it with respect to my testing data, let me try it out. Instead of doing this model on the training data, let me do the prediction on the test data. Fit initial radial. I want to do it on the testing data. So when I'm trying to do it on the testing data also, I get these are the trues, these are the falses. Right, again on the testing data, these are the true, these are the false. And if I have to go ahead in terms of identifying again what is the error rate or what is the layer of accuracy, I can very well create a table. The only thing is instead of y, I'll use it as test y. So in this case also the error is coming out to 32 out of 58. So the error rate is almost 55% with this kind of a model when I'm using the default parameters. Similarly, with respect to the negative also I can do the testing, right? So with respect to the negatives, if I want to implement the same model, right, we have implemented with respect to positive, but let's say I want to implement this with respect to negatives. Again I can take the same model, but instead of calling this on the train data, I will take it as negative. On this negative, I will be taking all the rows, but I will consider only the columns 1 to 6. Right? I'll consider all the rows negatives 1 to 6. All the rows 1 to 6 columns to do the prediction part. So for all those things, here it is working out to. So you could see there are a good number of falses and a few number of trues in the overall process. So if required again, I can very well create a table with respect to the negatives. If I want to test this model, I am going ahead with the spread initial radial along with I'll take negative and I'll consider only the 8th column, which is containing all the negative false values itself. So probably let's see what is the table typically looking like. So you are seeing that 277 are correctly classified, only the 95 are wrongly classified, resulting in 95 out of 277 plus 95 working out to 372. So overall resulting in a 25.5% error rate altogether. And all these things I can very well test it out using the confusion matrix as well, wherein I can get much more advanced detail. But before I go into that whole process, now I want to improvise the model by getting into different values of gamma and nu combinations. Right, I know that I should try out. So here the gamma is being considered as 1 by 6 and nu by default is considered as 0.5. So now I want to change that set of values by taking different values. I am doing the tuning of the model now. I will take different values of gamma, right? I want to take the different values of gamma and different values of nu, and I want to go ahead with the entire simplification package. So this is where I am taking the different values of gamma. So I'll take it as a sequence, let's say from 0.01 to here it has come out to 1 by 6, right? So probably let me take it up to 0.5, whereas the increment that we are considering by, let me take it as 0.02 or 0.01. So many values of gamma I can consider. Similarly, nu also, let me take different combinations. Here it is 0.5. So let me take it as 0.01 to zero point 0.1, right, or probably 0.01 to 1 by 0.05. So this 0.01 only let me take. I'll take different values of nu and gamma, and I'm also looking at the total length of gamma, so which is coming out as length of gamma. So I can get n underscore gamma as 50. Similarly, n underscore nu, I can take it as length of nu, which works out to n underscore nu for me is 100. So the runs for me, so I'll take different kinds of combinations. Probably this looks too big. Probably I should try just for this is just a this is just for understanding. So let me do one thing. Gamma, let me just bring it down. The gamma and nu, let me bring them down to 0.01 to 0.05, and nu also let me bring it down to 0.01 to 0.05. I'll have a few, but you have to try different kinds of combination. So based on that, now your n gamma, now it can't be 50 anymore. So let me repeat the process. The n gamma is length of gamma, which is 5. N nu also is the length of nu, which is 5. Based on that, now the runs for me is just a multiplication of these two. So I'll take 5 into 5, 25 different combinations of gamma and nu. Different combinations of gamma and nu. So the run should be around 25. So we'll start the process now. We'll do loop for different values of gamma and nu. What is the level of error that is coming up? So that's where I'll say count gamma I'm starting at 0, and even the count nu also I'm starting at 0. So I'm creating two new variables wherein the counting process for each one of them is going towards the zeros. Now we will be looking at we will be trying to compute the gamma, the nu, and the performance of each one of them, and we will be storing these three results. So the three results which we are considering in this case are the values of gamma, the values of the nu, and the performance in each of the cases. So that's where we are taking the results that we are going to get are 1 to 3 times the runs. So if we have runs of 25, we will be getting 75 results altogether, 1 to 75. And we are saving those 75 results as a 25 by 3 kind of a matrix. So that's where we are setting this dimension of it, the dim of the results, we are setting it as runs comma 3. We require 3 columns. The whole data we are considering in the form of 3 columns and 25 rows. And the column names for each one of them, for each of the results, the column names we are considering them as, the first one is going to be gamma, The first result that we are going to get is the gamma. The second result we will be getting is the new, and the third result we are going to get is performance. So based on that we are going to decide which gamma, which new value we are going to consider. Basically it's like you are experimenting with different values of gamma and new. So initially we'll start the process where I am setting some temporary variables I, k and count. So I am setting it to 1, k also I am setting it to 1, and count also I am beginning it from 1. 3 temporary variables. Now this whole loop is what is created for different values in new. I'll consider the different values of new for each value of new, for each value of gamma. So it's a kind of two loops that we are creating for value in new. So we have the news. So we are talking about for value in new. So new is having a values 0.01 to 0.05. So we will say for value in new, and similarly I will also consider for value in gamma. We'll take one in new, one in gamma. So for each value of new, for each value of gamma, that is what it means. So we are trying to print, just for understanding, we are trying to print gamma of I. So basically for each value 1, 2, 3, 4, 5, which will get printed as 0.01, 0.05, and at the same time I am also getting print new of I. I am also printing the value of new. So I am printing both of them. Then once along with the printing of these two, for each loop I am fitting an SVM. So I am creating a fit where I am considering SVM as a model, wherein I have my training attributes, which is train data, that is my training attributes. Y, I can very well set it equal to null. I am not considering my value of Y. Type, I have to set it as one classification. For each different, earlier we have done it with the base value where gamma is 1 by 6 and nu is 0.5, but now we are trying different values of gamma and nu. So we are repeating this model n number of times, right? So the new value in this case is coming out to nu of k. The new value I am considering it as nu of k. So in some one case it would be 0.01, then 0.02 and so on. And the gamma value will be gamma of I. So this is also a kind of a loop that is happening. And the cross validation will take 10 at a time. So this is the whole process that is going in terms of the fitting of the model. The model is fitted out here. Now we will get the result because we have got the SVM model fitted. We will get the gamma of each one of them. We'll get the nu of each one of them. And we are also going to get the performance. Earlier also when we have run the model, if we see, there is a performance that is going to showcase. Right, so here it did not shoot up, but even the performance of the model we can get using the dollar. So what I can very well do, I'll take the results of the first one, which is the count. Initially it is 0. So count comma 2. Initially we have set it to 1. So count of 1 comma 2, which is nothing but the gamma value. Or probably we'll go with count of 1, count comma 1, which is the first one is the gamma value here. Results count comma 1 is actually the first value that we are going to get is the new value. So this is where I can very well take fit dollar new. count of results comma 1 result equal to, sorry, this whole process is gone. Now again let me start the whole process for so we are first printing the values of gamma, we are printing the value of nu, and after that the fitment is typically done. But now the results I have to equate it to nu. What is this comma? So this is equal to nu. Similarly, the results count comma 2, this is equal to fit dollar gamma, and results count comma 3 goes to the results 3 is coming from the total accuracy of the model. So fit dollar tot dot accuracy. So these are the three things from the model we are assigning to the three columns, and based on that the count is typically incremented. The gamma's count is typically incremented. So from here the count of gamma is typically incremented. So count gamma is actually becoming count gamma plus 1. So you can try out the loop, the logic altogether, and from here we are actually increasing the overall count also. So it's becoming count is becoming count plus 1. So 1 is becoming 2 and so on. Even my I value, which is the gamma, actually is increasing with I plus 1. So this is the whole thing that is happening. The gamma loop now I can very well close. Now I am getting into the new loop as well, and again for the once I am coming out of the loop, the I would again set back equal to 1, whereas the k would typically increase from k to k plus 1, and this is where the whole looping process will be accomplished. So we are getting all the different possible values of the entire process. We are getting the values of, so actually we have to increment. I think looks like we have got the values of nu and gamma. So it looks like only the values of nu has been applied, because once we have fitted the results, right, I should end the loop somewhere. So we can very well get, so if I am typing in the results, yeah, these are the results that are coming up. The gamma, the nu, all kinds of combinations, the performance of each one of them has typically taken the shape of a data frame. So the gamma, the nu, the performance. So wherever I am looking at the maximum performance, so the performance is coming out to be the maximum here. So with results, I really want to see where the performance is equal to the maximum. I'm taking the subset of performance where the performance is equal to the maximum of performance. I have to equal with a double equal to, where it is equal to the maximum of performance. So it shows that with results, I'm taking a subset of performance where performance equal to the maximum of performance. So this has to be a data frame, looks like, right? Probably otherwise let me take the results as dot data dot frame of results. Initially let me convert it into a data frame, so that now let me see if I can use the width function directly. Yeah, so I get that it is 97.01 is the performance, and corresponding to that I get the gamma value as 0.03 and the new value as 0.01, right? So those are the gammas and the new values that I would like to use as a part of my new model. So I'll say fit new. I'm just giving you the process. Now you have to play around with the different values of gamma and new. Now I am using the new model SVM, where again I am going with train data as my input. The Y I will take it as null, and then I can look at the type as one classification. The type I am taking it as one classification. Now the new value I should be taking it as corresponding to this. Zero point 0.01 is the value of new, and gamma value I should be taking it as 0.03, and the cross validation I'll take it with 134. Now based on this I'm fitting a new model. So this is the new model that we have got. Fit new. In this case there are only 9 support vectors. Gamma is 0.03, the new is 0.01, and based on that I can again go ahead in terms of doing the prediction with respect to my training data as well, right? So probably a pred new, right? And in this case it's the radial function. So I'm using pred new, wherein I am using the predict function, and fit new is the name of the model that I have, and we'll use it on the training data itself. And it comes out that the pred new, this time the pred new is working out to a large extent, everything is coming out to be true. So the pred new has done quite a decent job out here, right? Looks like very few falses are there. So when I'm executing this model on the training data, at least the accuracy of the model is coming out to be much appropriate. So table, when I am doing it with pred new, when I am creating a table of pred new along with the original data, which is positive and the 7th or the 8th row from positive, or I can directly take it as test train Y. Train Y is containing, okay, positive and negative. So probably let me take it from positive itself. From the positive I am taking the 8th column. So okay, it has to be from the training data itself. So let me create it from the train Y. Let me create it with respect to train Y itself. So here it says 130 of them are correctly classified and only 4 of them are wrongly classified. So the error rate is 4 by 134 when I am doing it on the training data, 2 out of 2.98%. But the same thing, now if I am doing it on the testing data as the first thing, right, if I have to predict the same model on the testing data, let me see what is the result. So you will get the pred new on the testing data is working out to almost everything is coming out to be true. Hardly I could see 1 or 2 falses again. So which means even when I am trying to test it on the testing data also, the model is looking quite comfortable. The test Y. only 3 misclassifications. So 3 out of 58 lands up as the error part, hardly 5%. Now if I try to do this model completely on the negatives to see how the model typically has to come out, instead of using the test data out here, I'll do it on all the negatives, right? So I'll not use the test data here. I'll take it as negative and I'll consider all the rows, but columns wise I'll consider only 1 to 6, which are the attribute based columns out there. Based on that, the new model, and remember there all the values are negatives. So but here there are a good number of trues and falses that are coming when I am applying this model to the negatives out there. But let's see, if I have to do the table, right, if I have to do the table using the pred new which we have got, along with from the negative I would consider all the rows only the 8th column. So from there I am looking at the table. It comes out that 281 are correctly 281 are wrongly predicted as true. There are so many truths, whereas only 91 of them have been correctly classified as false when I am using the model for the prediction purposes out there. So that is where the error rate is typically lying, and that is how I can very well talk about the accuracy of the model. And more, if I really want a little bit more regarding the accuracy of the model, I can very well create a confusion matrix with respect to the test data. So this one I can test matrix. I'll call this as a test matrix where I am considering the table between the predict new and this one. So I am taking this as a test matrix, and I can take the confusion matrix from a caret package. So I'll install the caret package where I can take the confusion matrix. So I'll say install.packages caret, where a better representation of the confusion matrix also can come out. So I can very well combine both the positives and negatives and I can test out, or I can very well test it out only on the negatives. All kinds of scenarios can very well be tested until where I can improvise the overall accuracy of the model. So I will load this package library called caret, and on this particular package I want to introduce the confusion matrix. So we'll use this function called confusion matrix, which gives me slightly more details, right? I am considering the data as, so if I want to do it on the training data, I can very well go ahead and do it. If I'm doing it on the testing data, I can very well go ahead and do it. So whatever is the model that we have got, test matrix, and from there I would have to indicate what is positive. So positive is true. If I am giving this as the input to this confusion matrix, so here actually all of them are coming out to be false. That's the reason the confusion matrix is not able to give me any kind of a result. So if I set it equal to false, now here we don't have the values associated with true or false, the actual values. So probably let me take this particular model then with respect to the entire data, right? Let's do one more thing, the predict let me take it not with respect to negative or positive, let me take it with respect to the entire diabetes, right? And now we will create the table where I am taking prednew, and so with this particular prednew, we will again call it as false or negative, right? Where if else prednew, if else prednew equal to true, we will call it as positive, else we will call it as negative. So let's see what has come out as prednew. Some of them coming out to be positive, some of them coming out to be negative. Now I will take the table directly. In this table, I am considering prednew as the predicted values, and the actual is coming out as diabetes with all the rows and the seventh column. So let's see what is this table talking about. So this is the table: negative 91, 185, positives 281 and 7. So there is a big amount of error that is coming out in this process out here. So on the top of this, let me call this as conf matrix, conf mat. So I am taking this table as a part of the confusion matrix so that I want to perform the in-depth testing on this confusion matrix. So I'll say confusion matrix, wherein the input that I'm giving to it is the conf mat, which is the confusion matrix itself, and the positive will be set to POS. Positive is set to POS, and based on that I'm trying to understand the confusion matrix. Overall, the accuracy of the model is only around 48%. It can lie anywhere between 44 to 53%. That's the kind of accuracy of this model going with this one classification, right? The kappa value is much lower. So you can look at a different way of interpreting all these things. I have a separate video talking about each one of these values coming out of this confusion matrix, which is telling you the real accuracy of the model. Here you could see that the real accuracy of the model is hardly to the extent of 48%, right? I want this number to be as high as possible if I have to really assess that this model is good enough for the prediction purpose. So that's how we can very well go ahead in terms of doing a novelty detection on your data, and based on that doing the classification of the models also quite comfortably using the one classification support vector machine, right? So these are the entire things we have done. We have classified one of the categories as one classification class. I think we have done all these things. Find the best cross validation performance. The maximum performance is what we are more interested in. Then find the optimal model, and based on that try getting the values of the parameters. Use that for your prediction on the test data, and we are creating tables for training data as confusion matrix, testing data as confusion matrix. Use the confusion matrix method from the carrot package and try assessing the various statistics. The kappa is a much better measure of the accuracy of the model, but it's hardly around 15%. So probably I can very well omit out this particular model because the classification of it is nowhere close to good. So we can very well try out different possible values of gamma, nu to see if there is any kind of an improvisation of the model. We have got the best possible values of nu and gamma itself. So we have to understand for this particular example, one classification SVM did not provide any kind of a support for us. and there is a very high possibility that the support vector machines will be very sensitive to overfitting, as we have seen in this example quite clearly. All right, so that's what I wanted to take up as a part of this session. Right, we had a detailed understanding of CSVM for binary classification and one classification SVM, especially for novelty detection purpose. If you have any further queries regarding the same, you can very well get in touch with me by giving me a call on the number that I have provided below, or you can very well send in an email at vamsidhar@pagegurus.com. Thanks a lot for listening to this session. Thank you very much.